Hello students, welcome back, and let's go back and prove Hensel's lemma. Goes like this: P is a prime and K is a positive integer greater than or equal to 1, and f of x is a polynomial with integer coefficient, and R is a solution of this congruence. F of x is congruent to 0 modulo P to the K minus 1. In other words, f of R is congruent to 0 modulo P to the K minus 1. I'm highlighting this because we will use it shortly. Then we have, I still didn't correct it. Sorry about that. We just did part A, the main case. If the derivative evaluated at R is not congruent to 0 modulo P, then we have unique solution. R plus T P to the K minus 1 is congruent to 0 modulo P to the K power, where T is this. And then that's non-zero here. Therefore, inverse exists. And then f of R is congruent to 0 modulo P to the K minus 1. In other words, P to the K minus 1 power divides f of R. That's what this means, right? That means f of R over P to the K minus 1 power is an integer. So f of R is P to the K minus 1 times some integer. It's a multiple of P to the K minus 1. And that's some integer here. So let me highlight this in green because it came from this green. This came from this red, and this came from this green. And then one more thing. Let's see. Let's come back to this. Mod P to the K minus 1 power, this thing is congruent to 0. So adding 0 will not change anything. But mod P to the K power, it is meaningful. And in this particular t value, we have 0. And that t is unique. Uniquely this one. And how did it prove it? We began with a Taylor series expansion. Taylor polynomial rather, because this is polynomial, we don't need infinite series. And then quadratic or higher should all disappear because P to the K power divides all the higher power, P to the K minus 1 to the second power or something. 2 times K minus 1 is greater than K, and so on and so forth. So all these higher parts, those are all zeros. All those are zeros, so we don't need any of those. And then what's left is congruent to 0. That's what we have to prove. But what does that mean? That means subtract one from the other, and that thing is congruent to f of negative r, and then flip this one to the other side. Yeah, as we did in green. So divide everything by P to the K power. This one. This one. So we get green, that's an integer. And then divide this one. This one. So we get t is precisely that, nothing else. Therefore, we have unique solution. And we can find that unique solution through this P. So this thing is going to be useful when you actually solve an equation. Okay, that was a brief review on the proof of part A. Let's go to part B. In case the derivative is 0 and f of R is also 0, in that case, from Taylor expansion here, let's see. Derivative is 0, so that 2 is 0. All these are, of course, 0. And then the derivative is 0. And then f of r is also 0. So the derivative is 0, as highlighted here. So that's 0. And then this one, f of r is 0, so that's 0. And then all these, they're always all zeros because t to the k power will divide all those. So that's what you're going to get. These are all zeros for the same reason that we discussed in part A. And that's 0 because derivative is 0. And finally, f of r, that 2 is 0 because of the new condition. So yes, all 0 for any t. So we have multiple solutions. T can be anything, but of course, we got up to p to the k minus 1 power, so t will be 0, 1, 2, 3, 4 up to p minus 1. So there are p solutions for given r. Next, derivative is 0, but f of r is non-zero. In that case, from Taylor's theorem, well, these are all zeros for the same reason. P to the k power divides all those. And then the derivative is 0. Same thing. We're using red for the derivative condition. So that's 0. And then f of r, that's non-zero. So this is non-zero. And then otherwise all 0. So no matter what we do, this is non-zero, so we have no solution. So we went through a couple of trivial cases, and then this is a main case. And speaking of trivial, if I start from k as 1, then what do you have? K is 1, 1 minus 1, so this is 0 power. And then this thing is p to the 0 power, so modulo 1. So this is really trivial. Modulo 1, it's everything is the same. Modulo 1, everything is all 0. So all true. So case 1 case is not interesting, but it's true anyway because we only have 0, only one integer, modulo 1. So everything makes sense. Everything is true basically. So people do not really consider it, but hey, it's true anyway, so I just wrote it like that. So we have those 3 cases to consider, but these 2 cases are relatively not useful. This is a main case that we'll have to use. And how do you use this? Well, here we go, Hensel's theorem. So f of r is 0 and f prime of r is non-zero mod p, then the 0 of modulo p to the k power comes from this recursive definition, recursive equation. Let's see, do we have enough time to prove it? Okay, let's try. Here, f prime r negative 1 power is the multiplicative inverse of f prime of r modulo p, not modulo p to k power or k minus 1 power or anything, modulo p. And then that's valid because of this. Okay, all right, how to prove it? Well, there's nothing to prove when k equals to 1. And we go ahead with induction. Apply the conclusion from k minus 1. So conclusion is true for k minus 1. And then apply Hensel's lemma. So f of rk is f of rk minus, let's see, what's Hensel's lemma? Case 1 here. Let me copy and paste this thing. That's what we are applying. And then here, let's see. Yeah, this one here. No, this entire thing here, which I'm highlighting. Oh, I'm running out of color. Let's highlight it in purple. Is this one here. P to the k minus 1 power. No, I need negative as well. This is positive. So we can rewrite it as positive, and then we put negative here. And then f of rk minus 1 over p to the k minus 1 power, and then p to the k minus 1 power again here, so that no change. And consequently, this entire thing, sorry, there was a bit of a connection problem, so let's come back and resume. So rk minus 1 goes here in place of r in Hensel's lemma, and then this entire thing, as highlighted in purple, is p to the k minus 1 power. Now, in order to get p to the k minus 1 power, we divide it and then multiply it again. And can you divide it? Yes, we can, because f of rk minus 1 is f of rk minus 1 is a solution of the previous generation. So that is 0 of modulo p to the k minus 1 power. So it is divisible by p to the k minus 1 power. So this entire thing is indeed integer. And that's where we use the inductive hypothesis. You see, this thing here, f of rk minus 1, this one here is the solution, rk minus 1 is a solution of the previous equation of the congruence of the previous generation, modulo p to the k minus 1 power. So this is congruent to 0 mod p to the k minus 1 power. So p to the k minus 1 power divides f of rk minus 1. So the fraction is actually an integer. That's where we use the inductive hypothesis. So Hensel's lemma, and then force this p to the k power out and then divide. But division makes sense because of the inductive hypothesis. And then everything is okay. Hensel's lemma, by Hensel's lemma, this is 0 for this thing is t. And that's basically what we have over here. Consequently, we have this mod p to the k power, congruence to 0, mod p to the k power, and that's what we wanted. Okay, tricky here, tricky there, but we went through all those. And if you understood all those, great, but majority of the students probably didn't. In that case, you can read through the notebook, or better, you can go through the textbook. And even if you could not follow everything, that's okay. I mean, come on, this is number theory. This is 3000 level course. So understanding everything probably is not going to be possible to everybody. And that's why these are optional videos. Okay, all right, we are done with lesson 7.